Hello again. This lesson is called Investigating Gases in Syringes. During this lesson, students will be using this syringe and exploring gas matter and trying to make sense of what they see and feel using a model. Now, to do this lesson, you will need the class pack of syringes. Students will be working in pairs investigating these syringes. And you will start the class by showing them the syringe and how to properly squeeze and open up the syringe. And allow students a few minutes to explore these syringes, specifically asking them to observe with both their eyes but their sense of touch or feel about what is going on. So one thing you might have students do is compress the syringe to sort of feel what is coming out, which is of course air, gas. Another thing that we want students to experience is to attempt to compress the syringe with their finger over the top, because what they will observe is that as they squeeze the syringe, the force needed to compress or squeeze that syringe will increase. They'll also feel a lot of force on their little finger, and then if they let go, they'll observe that the compression tube will actually sort of push back, right? Because we will be asking them questions around why they think that is happening. They may also complete this again, compressing and then letting go all of a sudden with their finger, and they'll hear that burst of air pass through. At this time, we'll want to turn our attentions to the student notebook, where they will be modeling what they observed about the gas in the syringe. You'll notice that in the student notebook, students have a before compression model and an after compression model to complete. As teachers, we'll want to set the stage for them by asking them to again zoom in on what's happening at the very, very small level inside this syringe. This is one of the cross-cutting concepts around scale and quantity and measurement that we want to hit home with our students, is that natural objects do occur and can be modeled and explained at the very small scale. So because these are gas particles, students are going to want to think back to the model that they observed in previous lessons around how gas particles behave and interact with one another. They'll hopefully remember that particles in gas matter are spaced out, and they are spaced out randomly, so they don't necessarily aren't perfectly evenly spaced, and they're not all bunched together, but they are all over the place. Now, students may also want to include in their models some demonstration that these particles are moving. They can do this in a variety of ways, all of which can be embraced or encouraged at the beginning, but might want to be talked about collaboratively in groups around what sort of methods might be best. For example, some students might show that particles are moving either with these little wiggle lines, and they might even say that the more wiggles they have, the faster that particle is moving. But those wiggles don't necessarily demonstrate direction. A more effective tool for demonstrating motion might be force arrows. Force arrows tend to demonstrate strength and direction based on what direction the arrow is pointing and how long the arrow is. So this is a good way for students to model that there is different speed and different direction associated with their particles. Again, it's not 100% necessary for students to demonstrate this in terms of what is expected of a fifth grader, but here in our classroom it's a great way to really talk about how these particles are interacting with one another, and it should be encouraged where students want to do it. Now, what's important here is that we think about how what we've drawn in this before model is going to change when we get to the after model. So one of the things you'll be asking your students is to think about how many particles there are in the before model compared to the after model. This will help us get to that other idea around the conservation of mass and conservation of matter, this cross-cutting concept, scale and quantity idea. It's also going to help us, or help our students, construct explanations around why they feel what they feel when they add their fingertip to the end and compress, or what is going on with the compressional tool of the syringe, which tends to push out when we start, when we release our thumb off that compression. When we do draw these particles, so again we should be drawing, students should be drawing the same. When we see students that don't have more or less particles, or when they have more or less particles, we should ask them about why they chose to have more or fewer. We should also ask students who did have the same amount, that same question, to make sure that they understand why they did it. Could just be random. I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here. I got 3, 6, 9, 10. Oh, probably going to need 2 more. And you'll notice that when I draw in 12 more particles, well, they are a lot more tightly spaced, which means all that bouncing around, well, they're going to knock into each other. They're going to push on the different sides of the syringe. They are going to be knocking around. And that's the idea that we want to convey to our students, or that we'd like our students to convey to us and to one another, to help explain what they observed, that sort of bouncing back, that pushing back of the gas particles that were invisible, and could argue that there might be nothing in there, when obviously that's not the case, based on the forces that we feel on our finger and on the syringe top. That's what your challenge is as a teacher through the remainder of the class, to get students to construct these models, share their explanations in the column to the right, and then work with one another to sort of build consensus around which kinds of models are better than others, and which ones might they want to use moving forward in future modeling experiences. In conclusion, students will be building, using, and revising simple matter models to predict and describe the observed phenomena of the syringe being compressed and then pushing back on the user. We use this lesson to help students develop the larger understanding that matter of any type can be divided into particles too small to see, and we'll do so through the lens of the cross-cutting concept that natural objects and observable phenomena exist from the very small to the immensely large scale, which often cannot be observed directly. This lesson will help students reach towards achieving the standard of using a model of matter made of particles too small to be seen to explain common phenomena in our world. This has been a production of the Burlington, Massachusetts Science Center.